Okay, in 2.6 we're introduced to this normal distribution. And it's really quite interesting. So again, the whole idea is that if I take samples and find their average, okay, so I do this over and over and over again. I won't always get the same average from those random samples, but what I'll find is that as I do that, I could make a, and this time I'll actually make a histogram where things are connected like that, where, you know, this is the actual mean of wherever they whatever population they come from, and we saw that in our project in module 2. We did exactly this. We sampled a bunch of times and got averages, and they look like this. Okay, well, amazingly, people have studied this and so forth. We have a great, in theory, and that was the central limit theorem. What we know is that actually they follow a particular curve, and we know what that curve is. We know that curve, this is a curve f of x that I can plot on a graph, and what we know is that depending on mu and then this thing we call our standard deviation, so f of x equals, it is 1 over the standard deviation, sigma, the population standard deviation, times the square root of 2 pi, e, the number e, 2.71819 something, and so on, to the negative 1/2 x minus mu, that mean there, over the population's standard deviation, all squared. Amazing. So that is what the curve would look like if you tell me the mean and standard deviation of a population, well, actually, I guess I need to be a little careful there. That's sigma. In the case of our sampling distributions, it would be the standard error, okay, which is a standard deviation, but it's it's the standard deviation of the samples, the sampling distribution. So this sampling distribution, so I'll call that sigma standard error. The sampling distribution that we could get by running Excel over and over and over again to produce that thing, it fits that function, and I could get Excel or some other graphing thing to graph that, and it would just be that bell-shaped curve, and so that's what we'll be working with. At this point, our distributions pretty much just look like this, and we know we can put mu in the middle of it. This is supposed to be symmetric. And what we find is that these have a really interesting property, okay? And that is that really only up to scale, it's just scale. No matter what I pick for mu and sigma here, that if I mess with the scale that I'm plotting on, all the curves look the same. Now, what do I mean by that? Well, if we talk about standard deviations, and I could do this with more pieces and so forth, but here, you know, if we take this distance here as one of these standard errors or standard deviations, and so if that was mu, this is mu plus sigma, then this is mu plus 2 sigma, and mu plus 3 sigma out to here, and do the same thing on this side with minus, so mu minus our standard error or standard deviation, mu minus 2 sigma, mu minus 3 sigma are there. That actually, if this is how I talk about the number line, if I talk about it as the mean being here, 0, and then how many sigma I've gone out here, you know, so I've gone out 1, 2, 3, or minus 1, minus 2, minus 3. If that's the way I talk about where I am with this distribution, the numbers are always the same as far as how much of the population is in each portion. So what we know is, and it's symmetric, so each of these is 0.34, or in between there is 68% or 0.68. So that's always true, and we'll do a couple quick examples of what we mean there. And then between plus and minus 2, there's always about 95% of the data, or 0.95, 95%. Now, so I have to do some quick math, right? So 68, 95 minus 68 is, 95 minus 68 is 27. And so half of that, this is 13 and a half, or 0.3135, 0.135, always. And then, if we go out 3 standard deviations, that will be 99.7% of all the population would be plus or minus 3 standard deviations. And so that's 4.7 between the two of these, so that would be 0.235, I think, and 0.235, like that, and that would be 4.7% between the two of those. And then everything else is out here, but that's not much, right? 0.3% of all of the population is out there. Now, how is this handy? Well, there are a couple different ways it's handy. One is simply that if I do give you things in some round numbers, you know, so if I tell you something like what, temperatures, we all have to take our temperature these days. So my, say human body temperatures have a mean of 98.6 degrees Fahrenheit, and then the standard deviation the standard deviation, actually, off the top of my head, I'm not sure. I could probably get on my computer and look it up. But let's say it's half a degree, or yeah, we'll go with we'll say half a degree, is 0.5 degrees. Okay, now what can I tell you then? Well, then I could tell you that 68% of people have a body temp between 98.6 minus 0.5 and 98.6 plus 0.5. So if I know it's a normal distribution, that says what, 98.1 to 99.1. Okay, so that tells me 68% of the people are in there. If I go up to 2 standard deviations, then I know 95% of people are between what the heck do we have here? 98.6 minus 2 times 0.5, or 1, and 98.6 plus 2 times 0.5, or 1. And so that gives me from 97.6 up to 99.6. And so that's 95% of the population. And so, you know, when we say, oh, like a temperature of 100.3, you know, well, where does that put us? And actually, I didn't look this up, so I don't know, but it's, you know, I'm just kind of going with, I have looked it up before, and so I was just sort of guessing here. But notice, by the time we get to 3 sigma, our top temperature, 98.6 plus 3 times 0.5 is 98.6 plus 1.5, which is 100.1. And I think, I don't remember I don't remember off the top of my head, but I think we want to report temperatures of like 100.3 or something like that. Oh, well, see, if I know this about standard deviations and so forth, then actually I'm guessing a good reason to go with something around 100.3 is, remember, this would be 99.7% of the population, almost the whole population, and then we toss in a little bit more on the left side, because this picture, here's 100.1, and if I go a degree and a half on the left of 98.6, well, that's a terrible 100.1, there we go, I'm at 97.1. Okay, but if we're asking, you know, sort of, and I'm going to go with 100.1, but if I said, okay, I'm going to set that you have a fever at 100.1, you know, well, that's actually kind of reasonable, because I know between these two lines is 99.7, so 0.3 is on the outside, well, so that's 0.15%, and this is also 0.15%, and so total for everything here I get 99.85%. I should put percent here, and these are percents. So 99.85% of all people should be, at least given my standard deviation here that I used, should be below a temperature of 100.1. So if you're above that, I'd say it's a pretty good chance you're running a fever, right? Because you are probably not in that group. Now, actually, many years ago when I was living in Colorado, I did not know her personally, but it was the friend of a friend. She had a normal body temperature of like 101 or something along those lines. So she rarely got sick because she just had a natural body temperature that was very high. So people do have these, but very few people have such things. And so that's where we can say, oh yeah, you are probably running a fever because you are probably not in this group. Okay? So that is kind of that rule of thumb. Some more to that rule of thumb, of course, is using the body temperature thing. I know 50% are at 98.6 or below. 50% are at 98.6 or above. Again, with continuous things, equality doesn't change things, so we would just say 50% in either direction from the 98.6. And, and that comes from the symmetry here, right? There's 98.6, oops, 98.6. And I know that, half is here, half is there, so 0.5, 0.5. Because it's symmetric. They look the same. And we can use that basic rule of thumb to just estimate things. I do that quite a bit when, if I'm thinking about standard populations and that sort of thing. I kind of, what's the mean? What's the standard deviation or standard error? And I can do a quick, what's 2 times or 3 times and so forth, and determine these rule of thumb numbers. Okay, but this is true no matter what the normal distribution. And so you see I was using the mean and the standard deviation or standard error. Okay, so that's rule of thumb and a quick introduction to normal distributions.